Hello friends, welcome to my lecture on variational problems with a movable boundary for a functional dependent on two functions. Let us consider the functional I by x zx, where y and z are two dependent variables and x is an independent variable. The functional is x integral x1 to x2 fx by x zx by dash x z dash x. Let us consider a point A x1 by 1 z1 which is fixed, and the other point B x2 by 2 z2 move in an arbitrary manner, or it moves along a curve, or it moves on a surface. From Euler's equation, the extremal can be attained only on the integral curves of the two equations delta f by delta y minus d over dx, delta f over delta y dash equal to 0, delta f over delta z minus d over dx of delta f over delta z dash equal to 0, because we know that the necessary conditions for the extremal in the case of more than one dependent variable are the two equations given by the Euler's equations here. So, the extremal can be attained only on those curves. Now, the general solution of these equations contains four arbitrary constants. Since x1 by 1 z1 is fixed, it is possible to eliminate two arbitrary constants. The other two arbitrary constants have to be determined from the necessary condition, that is delta I equal to 0, where delta I is the variation of I. Now, delta I is equal to f minus by dash delta f over delta by dash minus z dash delta f over delta z dash x equal to x2 into delta x2 plus f by dash x equal to x2 into delta y2 plus f z dash x equal to x2 delta z2 equal to 0 for an extremum. Now, if delta x2, delta y2, delta z2 are all independent here, then their coefficients must be 0, and so f minus by dash f by dash minus z dash f z dash x equal to x2 is 0, f y dash at x equal to x2 is 0, and f z dash at x equal to x2 is 0. Now, if the boundary point x2, y2, z2 moves along some curve, and the equations of the curves are y2 equal to phi x2, z2 equal to psi x2, then from y2 equal to phi x2 we have delta y2 equal to phi dash x2 delta x2, and z2 equal to psi x2 gives delta z2 equal to psi dash x2 into delta x2. So, from the equation 2 means this equation, what we will have is f minus by dash delta f by delta y dash minus z dash delta f by delta z dash into delta x2 plus f y dash delta y2 plus f z dash delta z2 equal to 0. Now, we have delta y equal to delta y2, since delta y2 equal to phi dash x2 delta x2 and delta z2 equal to psi dash x2 delta x2, this equation, okay, this equation we have called as 2. The equation 2 gives us f minus by dash f by dash delta y2 is phi dash x2 delta x2, and then fz dash delta z2 is psi dash x2 delta x2 equal to 0. So, let us we can write it as then R f plus phi dash minus by dash f by dash plus psi dash minus z dash into f z dash at x equal to x2 delta x2 equal to 0. Because we can collect the coefficients here delta x2 delta x2 delta x2. So, this is f plus phi dash at x equal to x2 is phi dash x2 and then phi dash x2 f by dash at x equal to x2 into delta x2. So, this is here and then minus by dash f by dash delta x2 it is here and then f z dash psi dash x2 into delta x2 is here and minus z dash f z dash into delta x2 is here. So, we can write like this and since delta x2 is arbitrary we have f plus phi dash minus by dash f by dash plus psi dash minus z dash f z dash at x equal to x2 is equal to 0. This is the transversality condition. This is transversality condition. When the point x2 y2 z2 moves on a curve, then this is the transversality condition for the extremum of the functional one. Now, along with the equations psi 2 equal to phi x2 and z2 equal to psi x2, this transversality condition gives the equations necessary for determining the remaining two arbitrary constants in the general solution of Euler's equations. Now, in case the boundary point x2 y2 z2 moves along a given surface, we know that the equation of a surface can be written as z equal to phi xy. So, in that case z2 will be equal to phi x2 y2. Now, z2 equal to phi x2 y2 and z equal to phi xy gives us the increment in z2, that is because x2 by 2 z2 is the moving point. So, delta z2 will be the partial derivative of phi with respect to x at x equal to x2 into delta x2, then partial derivative of y at y2, so phi y2 into delta y2. The variations delta x2 and delta y2 are arbitrary. Now, in this case the equation 2 will take the following form. Equation 2 which is f minus by dash f by dash minus z dash f z dash delta x2 plus f by dash x equal to x2 delta y2 plus f z dash this equation in this case will take the form delta z2 is, so since delta z2 is equal to phi x2 phi x2 means phi x at x equal to x2, okay. Delta x2 plus phi y at y equal to y2 or x equal to x2, then delta y2. So, let us use this here, then we can write it as f minus by dash. Since this is equal to this, we get f minus by dash, f by dash, and then here f by dash x equal to x2 okay, minus z dash, f z dash delta x2. Let us put the value first, f by dash x equal to x2, and then delta by 2 plus we have put f z dash. Let us put the value here, delta z2 is phi x at x equal to x2 delta x2 plus phi y delta by 2 equal to 0. So, we can write it as r f minus by dash, f by dash delta x2, f, it can be combined with this term here. So, we can write phi x minus z dash f z dash into delta x2 x equal to x2 plus, and this term can be combined with the term here. So, we write f by dash f by dash plus phi y f z dash at x equal to x2 delta by 2 equal to 0. So, we get f minus by dash, f by dash plus phi x minus z dash f z dash del x equal to x2 delta x2 plus f y dash plus phi y f z dash x equal to x2 delta by 2 equal to 0. Now, since delta x2 delta by 2 are independent, we get f minus by dash f y dash plus phi x minus z dash f z dash at x equal to x2 is 0, and also f by dash plus phi y f z dash equal to 0. So, these two equations along with the fact that x2 by 2 z2 lies on z equal to phi xy, we get z2 equal to phi x2 by 2. So, these equations enable us to get the remaining two arbitrary constants in the general solution of the Euler's equation. Now, let us take the example on this article. Let us find the shortest distance of the point 0 to 4 to the straight line given by x minus 1 over 1, y over 3, z over 4. The equations of the line are given in the symmetric form. So, we know that I y x z x, okay, is integral because the x1 point is 0, this is x1 y1 z1 which is a fixed point. So, x1 is 0 here, x2 y2 z2 is a variable point which will lie on the line given here. So, and then we want to find the shortest distance, and we know the formula dx square plus dy square plus dz square under root, that is ds. So, when we write it as, we write ds over dx into dx, ds over dx can be written as square root 1 plus dy over dx whole square plus dz over dx whole square. So, we have written it as under root 1 plus y dash square plus z dash square into dx, and the limits of integration are x1 equal to 0 and x2 is a variable x. So, x1 0 goes 0 to x2. So, here f x by z by dash z dash is equal to square root 1 plus by dash square plus z dash square. Now, the equations of the lines x minus 1 over 1 equal to y over 3 gives us y equal to 3x minus 3. So, we can write it as a function of x, say phi x, and x minus 1 over 1 equal to z over 4 gives us the other equation z equal to 4x minus 4, we can denote it by psi x. So, y is a function of x and z is a function of x. Now, the Euler's equations are for the extremal, the Euler's equations are f y minus d over dx f y dash equal to 0, f z minus d over dx of f z dash equal to 0. So, since our extremal is since our f x by z y dash z dash is equal to square root 1 plus y dash square plus z dash square. F is independent of y, so its partial derivative with respect to y is 0, and therefore f by minus d over dx of f by dash is equal to 0 gives us 0 minus d over dx of f by dash. Now here f by dash if you find, then f by dash is 1 over 2 square root 1 plus y dash square plus z dash square into 2y dash. So this is y dash divided by under root 1 plus y dash square plus z dash square. Let us put it here. So y dash divided by under root 1 plus y dash square plus z dash square. So this is equal to 0. So first equation gives us y dash divided by, since derivative of y dash divided by under root 1 plus d y dash square z dash square to the power half is 0, this gives y dash divided by under root 1 plus y dash square plus z dash square is equal to some constant. Let us take this constant as C1, and similarly let us note that the fx by z by dash z dash is independent of z, so partial derivative of f with respect to z is also 0. Hence fz minus d over dx of fz dash equal to 0 gives us 0 minus d over dx of derivative of f with respect to z dash is 2z dash divided by square root 1 plus y dash square plus z dash square. 2 times. So this 2 cancels out with this and we get z dash divided by square root 1 plus y dash square plus z dash square is equal to 0. D over dx of this, d over dx of this is 0, so this is some constant, let us say C2. So we get these two equations, y dash over under root 1 plus y dash square plus z dash square is equal to C1, z dash over under root 1 plus y dash square plus z dash square is equal to C2. So let us divide these two equations, then we get y dash over z dash equal to C1 over C2, and C1 over C2 is another arbitrary constant, we can write it as C3. So y dash is equal to C3 z dash. Now let us put the value of y dash equal to C3 z dash in this equation. Z dash equal to 1 plus y dash square plus z dash square to the power half. We will get z dash divided by 1 plus C3 square z dash square to the power half equal to C2, or we can solve it for z dash. Z dash is equal to C2 upon 1 minus C2 square C3 square to the power half. So this is, let us call it as C4, is some arbitrary constant, we can call it as C4. Now this is dz over dx equal to C4. So z equal to C4x plus some constant C5, and y dash is equal to C3 z dash, we have y dash equal to C3 z dash here. So y dash equal to C3 z dash gives us z dash is some constant C4. So C3 into C4 y dash is equal to C3 C4, we can so this gives us, let us say this is C6. So then y is equal to C6x plus C7. So we get the expressions for y and z in terms of x. Now let us find the extremals. Extremals are given by equation 3 and 4, since the record extremal has to pass through 0 to 4. the line of shortest distance has to pass through the fixed point 0 to 4 and the point variable point x2 by 2 z2. We have by at 0 is equal to 2, and because by is a function of x, so and z is also a function of x. So by at 0 is equal to 2 and z at 0 is equal to 4. This is x1 y1 z1. By at x1 is y1 and z at x1 is z1, and similarly by at x2 is by 2. So by at x2 is 3x2 minus 3. By x is equal to, we have by equal to 3x minus 3. So by at x2 is equal to 3x2 minus 3 and z2 equal to 4x2 minus 4. So we get zx2 equal to 4x2 minus 4. Now what we have, z equal to c4x plus c5. So in this you put x equal to 0, x equal to 0, when we put what we get, z equal to 4. So c5 is equal to 4 and y at x equal to 0 is 2. So what we get is y c7 is equal to 2. Now zx2 is equal to 4x2 minus 4 and z is also equal to c4x plus c5, c4x plus c5. So c4 from here what will happen, z equal to c4x plus c5 means z2 equal to c4x2 plus c5, and so what we will get is c4 equal to, c4 we have already found, c4 no, c5 we have found, c5 is equal to 4. So z is equal to c4x plus 4, and let us this z equal to c4x plus c5 passes through x2 by 2 z2. So we get zx2 equal to, zx2 is equal to 4x2 minus 4 and z equal to c4x plus c5 gives us c5 is 4, and so that, and hence zx2 is equal to c4x2 plus 4. So what do we get from this equation and this equation? c4x2 plus 4 is equal to 4x2 minus 4. So we get 4x2 minus 8, c4 is equal to 4x2 minus 8 divided by x2, and then by x2 is equal to 3x2 minus 3, and also by x2 is equal to c6 x2 plus c7, and we have already found the value of c7, c7 is 2. So we can put here 2 and then solve these two equations for c6, c6 comes out to be 3x2 minus 5 over x2. Now since the point x2 by 2 z2 lies on the curve, the following transversality condition has to be satisfied: f plus phi dash minus bi dash f bi dash plus psi dash minus z dash f z dash x equal to x2 equal to 0. F is given to be under root 1 plus bi dash square plus z dash square. Phi dash, phi x is equal to 3x minus 3. Phi x is equal to 3x minus 3. So phi dash is equal to 3 and psi dash is equal to 4. So let us put these values here. So we get then 3 minus bi dash, f bi dash is bi dash over under root 1 plus bi dash square plus z dash square. Psi dash is 4 minus z dash, f z dash is z dash upon under root 1 plus bi dash square plus z dash square at x equal to x2 is 0. Now so when you take LCM here, under root 1 plus bi dash plus z dash square is the LCM, and then the numerator becomes 1 plus bi dash square plus z dash square, 3 bi dash minus bi dash square, 4 z dash minus z dash square. So bi dash square z dash square will cancel and we will get 1 plus 3 bi dash plus 4 z dash equal to 0. But bi dash is equal to c6. Let us see, bi dash we have seen to be equal to, bi dash is equal to c3 into z dash, and c3 into z dash was equal to c4. So c3 into c4 we defined as c6. So bi dash is c6 and z dash is c4. So let us replace these values there. So, 1 plus 3 by dash means 1 plus 3 C6 and 4 Z dash means 4 C4. So, this is equal to 0 as by dash is C6, Z dash is C4. Now, then okay, so let us see, we have 1 plus 3 C6, 1 plus 3 C6 plus 4 C4 equal to 0. In this we can put the value of C6 as 3x2 minus 5 over x2, 3x2 minus 5 over x2, and then we can put the value of C4 also. So, 4x2 minus 8yx2, and simplify, we will get the value of x2. x2 comes out to be 47 minus 47 by 26. So, x2 comes out to be 47 by 26. Now, C4 is equal to C4, here is C4 is 4x2 minus 8 by x2. So, let us put the value of x2 here, and we get the value of C4 as minus 20 by 7. C6 is 3x2 minus 5 over x2. So, we get C6 as 11 by 47, and then we get the value of by equal to by was equal to C6x plus C7. So, we get 11 by 47x plus 2, and Z is equal to C4x plus Z is equal to C4x plus C5. C5 is 4 and C4 we have already found. C4 is minus 20 by 47. So, Z is equal to minus 20 by 47 into x plus 4. So, these are the equations of the line of shortest distance. Now, so this shortest distance occurs along the straight line. Equations of the line of shortest distance can be put in the symmetric form. These equations, which are the equations of the line of shortest distance, we can easily put in the symmetric form, and the symmetric form is x minus 0 by 47 equal to y minus 2 by 11 equal to z minus 4 by minus 20. Now, the required shortest distance is integral 0 to x2 1 plus y dash square plus z dash square to the power half dx, and x2 we have found to be 47 by 26. So, 0 to 47 by 26, the value of C6 is 11 by 47, C4 is minus 20 by 47. So, we can put them here, take the square root and then integrate, we get the value square root 105 by 26. So, we got the equations of the line of shortest distance and also the required shortest distance. So, with this I would like to conclude my lecture. Thank you very much for your attention.